So the goal of the lecture today is I'd like to cover some background on variational algorithms. So these are near-term algorithms. I'd like to talk about what are various models of quantum noise in quantum circuits. And then I'm going to talk about some of my recent work, research work in doing circuit simulation using novel techniques. And I should point out that Leah introduced me as a professor at Rutgers. So I'm currently a postdoc at Princeton, and I'll be joining the Rutgers faculty in the fall. So here's an outline for the presentation today. So the basic idea that I'm driving to today is that we need to build better simulators. And these simulators are going to be useful for us to understand noisy variational algorithms. And so to understand this thesis statement, I'm going to talk about why it's important that we study variational algorithms. Secondly, I'll talk about what does it mean for there to be quantum noise in a quantum circuit. I'm going to talk about why simulating these algorithms is particularly difficult. And I'm going to talk about a novel technique using techniques that we borrow from classical AI, from classical inference as a way to simulate these variational algorithms. So let's go ahead and jump in. So the excitement about variational algorithms is that we believe that they're going to be the first demonstrations of useful quantum computing. So you might have seen variations of this type of graph before. So what this graph is showing is that over the course of the development of quantum computing technology, we're obtaining more and more useful qubits over the decades. But as we understand, if we are going to eventually one day run these algorithms that are so famous, like Grover's and Shor's algorithm, we need a huge number of qubits in order to provide the fault tolerance, in order to provide the error correction, in order to run those types of algorithms. And what's interesting is that we believe within the next 5 years, there's actually a whole different class of algorithms in the area of simulating quantum chemistry, doing things like optimization. And these types of algorithms, you only need a few in the order of 100 to 1,000 qubits in order to run them. And these are particularly exciting because these types of algorithms in optimization and chemistry will be good stepping stones for us to work toward eventually getting to the point of doing these famous algorithms like Grover's and Shor's. Okay.
In the plot, what's the split?
Splits?
At the 2015 to 2025.
So that split's just, it's like uncertainty, right? So this is kind of a cartoony plot, but what the idea is that if you were to project just existing resources up to current point 2020, you may see this continued trajectory. But the idea is that with increased effort and increased concentration throughout the world in quantum computing, you may see an acceleration in how quickly we obtain useful qubits. So that split is just it's just uncertainty. Okay. So let's go into a little bit more detail. So this is going to be about why we want to do variational algorithms and why they may be useful using in the NISQ near-term era. And the basic idea is that running variational algorithm, it's going to be a lot like using a classical computer in order to train a neural network, where the neural network is a quantum device. So this is a often shown picture of a type of variational algorithm. So this is specifically a variational algorithm called the Variational Quantum Eigensolver, or VQE. And the basic idea is that you break down the algorithm into two parts. So the algorithm and the computation proceeds using both a quantum computer and a classical computer. And in the quantum computer, what you're doing is you're trying to evaluate a type of objective function. So this objective function will be something that comes from, say, the optimization problem that you're trying to solve, or the quantum mechanical model of a molecule's property that you're trying to find. Okay, and the useful computation results of this will be coming from the parameters that make this optimization objective function optimal. And in order to find those optimal parameters, what you do is you use the quantum computer to evaluate those objectives, and then you feed them into a classical computer here on the right-hand side here. And the classical computer in this case is just going to run a classical optimization algorithm like gradient descent or Nelder-Mead. And the whole algorithm proceeds as we find better parameters for the quantum half. Okay. And so the reason that these types of algorithms are expected to be useful in the near term is that with this type of algorithm, because it's an optimization algorithm, we don't have to evaluate the optimization objectively perfectly. And so we don't have to rely on techniques like error correction in order to evaluate that objective function. And furthermore, we only need on the order of 50 to 100 qubits, at which point we may see useful applications. So just with only 50 to 100 qubits, you can start evaluating interesting models for molecule properties that classical simulations would just not be able to solve. And so these would be probably the useful cases in the near future. And as I said, there's a few important examples of these types of algorithms like QAOA, which is the quantum approximate optimization algorithm, and also VQE, which is an algorithm used for quantum chemistry. Okay. And so up to this point, just about VQE, this is just a very cursory introduction to what a VQE algorithm is, but happy to take questions if we have anything about that up to this point. Okay, so the next part of this talk now is that we're going to talk about why it's important to take into account noise or imperfection inside a quantum circuit, and what are some types of models that we use to model that noise. And quantum noise, intrinsically, what it is it comes from the property that the quantum hardware that we're running these algorithms on, they're intrinsically unreliable, right? So this comes from basically two types of phenomena. One is that the quantum state inside quantum computers, they're imprinted on really delicate states, on really of particles. And the whole environment, so the laboratory environment, heat, any stray particles in the vacuum, all of these environmental factors are constantly trying to bombard your delicate qubit state, and that's going to disturb the computation, the fidelity, right? And so that's one aspect of the noise. And another aspect of the noise is that in these algorithms, we're applying quantum gates with fairly high precision operations. And in practice, the laboratory equipment is not going to apply those gates with exactly the level of precision and the accuracy that you want to perform those gates. And so you will have over rotation, under rotation in each of the gates. And all of these imperfections are going to lead to quantum circuits. When actually run on the quantum computer, they're not going to match the original intended quantum circuits that we want. And so the next part here is a little bit of mathematical background, talking about what it is, that how we actually represent a noisy quantum state. Okay, and so what I'm walking through here is I'm going to take a hypothetical quantum state, just like a zero state, and we're going to feed it through a model of a quantum error. In this case, it's a very simple type of error called a bit flip noise. And what the bit flip noise does is that it has a 36% chance of taking your state and introducing an erroneous X gate to it. So the X gate will just change a 0 to 1 and change a 1 to a 0. And so at the end, your state is going to be what we call a mixture of two types of states. So it's going to be a 64% mixture of the correct 0 state and a 36% mixture of the incorrect 1 state here. And so you can represent these types of noisy quantum states as mixtures. But more generally, there's another way in the literature that we represent these quantum states, and the way that we represent that is called a density matrix. And what a density matrix does is it's able to represent in a single matrix these types of mixtures. And the way you compute a density matrix is you take each component of the mixture and you do a weighted sum of the components, where you take a outer product like this, a Kep-Bra product, and you sum them up. And so in this case, the mixture that we had here is now going to turn into a density matrix like this. And the nice property of this type of representation is that you're able to represent any probabilistic encoding, probabilistic mixture of quantum states in this way without having to break it down into component mixtures. But the trade-off is that while it's very nice and arbitrary in general, they're costly to store, right? So the dimension of the density matrix, its linear dimension on one side is going to be equivalent to the length of the state vector. All right, so if you had n qubits, it would take n 2 to the n number of states to represent that as a state vector. And it's going to be even more costly to represent as a density matrix, where you're going to take 2 to the n times 2 to the n elements to store the whole density matrix. So in general, it's very costly to do computation in this way. And so there's many different types of quantum noise. So if you go into the Nielsen-Truong textbook, chapter 8.3 gives some canonical examples of what are important types of noise. And basically there's two types. So there's mixtures and channels. So what mixtures are, they're the simpler type. So what they represent is that you're going to have a probabilistic unintended gate inside your circuit. So for example, a bit flip noise is going to introduce a unintended X gate in your circuit, and a phase flip gate is going to introduce a unintended Z gate in your circuit. And then also you'll find various types of combinations of these. So there's also depolarizing noise, which is a mixture of both X and Z type, and also Y type errors. And so you can think of these as a combination of both bit flip noise and phase flip noise. And so one thing to note about this types of simulation is that you can think of these as these gates, and so you can simulate them as ensembles of state vectors. And so in some sense, these mixture type, this first row here, is a easier type of quantum noise to simulate. Okay, so now I'm going to move on to the second row here. So the second row is a type of noise that we call channels. And what channels are, they are more suitable for representing if your environment is going to disturb your quantum state. And so one interesting property of this type of noise is that they're somewhat lopsided, okay? So for example, a amplitude damping gate, it's just like the bit flip gate in that it will change your quantum state in the X direction, but it's lopsided. So what a amplitude damping gate, what it would do is it would take a 1 state and move it down to a 0 state. But if it's already a 0 state, then it will just keep it in the 0 state. Okay, and it's precisely this type of lopsidedness that makes these types of quantum noise channels in this bottom row here a little bit more difficult to represent as state vectors. And so conventionally, in order to simulate channels, you have to resort to density matrices. Okay. So any questions so far, or anything relevant to the taxonomy of quantum noises here that I can answer?
Is the amplitude damping equivalent to the bias towards either 0 or 1, so one of the two states for a qubit, mentioned in the Ensemble of Diverse Mappings paper that Swamit presented at Micro a few months ago?
That's a good question. I don't know his paper in super detail precisely, but what I would check is you can go in and see what type of noise that he refers to. So one thing to note is that we understand depolarizing noise much better, and we're able to work with depolarizing noise much better than channel type noise. Okay. This could be for kind of two reasons. One aspect is that depolarizing noise, this upper row here, is a little bit easier to work with. And another aspect is maybe more physical, which is that if you talk to the device engineers, they tend to engineer the devices so that they provide an abstraction where the noise can be represented as depolarizing noise. But if you wanted to tackle most general quantum noise, then you also have to consider the lopsided types of noise on the bottom here. So I think that means there's questions in the chat box.
Yeah.
So I can take a look at the chat box here. Yes, so the question from Vincent is that, are the density matrices for channel noise non-unitary? There's a little bit, I have to go in and clarify the nomenclature here. So density matrices represent the quantum state. They represent a probabilistic quantum state, okay? The density matrices themselves do not represent the noise channel. So this is like the difference between state vectors and gate unitary matrices, okay? And then in general, if you want to represent quantum channel noise like amplitude damping, that operator, that mathematical operator, is not actually a density matrix. They're referred to as these things called Krauss operators. And so you can go to the Nielsen Chuang textbook. It has a definition and all the Krauss operator matrices that will tell you how to multiply the density matrices, multiply them against density matrices. And yes, in general, these matrices at this point might not be unitary. Good question. Okay. All right, so that was a very quick survey of quantum noise, so the important textbook examples of quantum noise. And next I'm gonna move on to the problem and the challenge of simulating quantum algorithms, okay? And specifically in this paper that I want to talk about, the challenge of simulating noisy variational algorithms. So first, it's useful to talk about why it's important at all that we do quantum program simulation, okay? And so there's many important reasons. So one aspect is that suppose you have a quantum algorithm and you want to develop it or test it against different inputs, but you don't have an actual quantum computer that is able to run your devised quantum algorithm. So it would be useful to use the current generation of classical computers as a way to study quantum algorithms, okay? And the second question is, okay, suppose you have a quantum computer and it's running a quantum program, but you want to understand whether or not it's performing as expected compared to some noise model that you devise. And so in this second use case here, it's important to do quantum circuit simulation because you want to compare the results of a quantum computer against the simulated results of a classical computer, okay? And the third reason is even more intriguing, which is the use case in the third reason here is you want to understand at which point we're actually doing useful and interesting quantum computing, stuff that purely classical computing would not be able to achieve. So this is the notion of quantum computing supremacy, where you're demonstrating and you can prove that you're using a quantum computer performing a procedure that no classical computer can perform. And in that case, you want to use classical circuit simulation in order to demonstrate that you cannot achieve that level of performance, right? And so specifically, one can imagine it's particularly important in the near future that we study the problem of simulating variational algorithms. So I mentioned that variational algorithms are going to be the first demonstrations of useful quantum computing. And in conjunction to developing the algorithm and developing the quantum computers, we also want the ability to simulate them efficiently, or as efficiently as possible, using classical computers. And so to address this challenge, we want to think about, so what is it special about a variational algorithm that makes it a unique simulation task? And so there's a few properties about variational algorithms that make it special. One is that you want to be able to simulate quantum noise, as we discussed. So you want to be able to capture the noisy properties inside the simulated quantum circuits here. And secondly, these circuits that the variational algorithms use tend to have a lot of qubits, but relatively fewer operations. And the second is more about the way that the algorithm runs. So we talked about how the variational algorithm, the way it proceeds is the quantum computer runs many times, each time evaluating an objective function. And each time it's going to be doing that evaluation with different parameters. And so it would be useful if our simulation technique is able to match that, be able to simulate the same quantum circuit many times, but each time with different set of parameters. And thirdly, is that in comparison to typical quantum circuit simulation techniques, in this context, we're not interested in the whole state vector, but instead what we want is just these samples that we draw from the wave function, a lot like the way that a quantum computer would draw samples from the wave function. And so we're going to compare those properties about variational algorithms and think about, okay, do existing quantum circuit simulators match up with those properties, right? And so there's a few important quantum circuit simulation techniques that I'm going to cover in this slide here. So one type of simulation is what we call Schrodinger simulation. And so this is the most typical type of quantum circuit simulation. The way it works is you take the gate operator unitary matrices and you multiply them against these long vectors that represent the state. And this is the simulator that you'd find in Qiskit, the simulator you'd find in Google Circ, and so on. And if we think about, okay, does it match up with these properties that we're interested in? And we'll find that, okay, because state vector simulations, the way that they store the state is in these really long state vectors, in general, it's going to suffer if your circuits have a lot of qubits. This is why quantum circuit simulation in general does not scale. And secondly, if you think about, okay, if we're going to do the simulation many times over, because it's a variation algorithm, can we somehow preserve the structure and the computational results from one run and reuse that for the next run? And in general, for state vector simulation, if you're doing matrix vector multiplication in the way these simulators do, in general, no, it's not going to be able to do that type of repeated simulation. But because for the third part here, because you find the whole state vector, you're able to sample from the final wave function completely. Okay. And for the rest of the slide here, I'm just going to put this up. There are also various other types of simulation techniques that are very important. So one type is via these mathematical operations called tensor network contraction. This is another way that we can do quantum circuit simulation. And finally, more recently, there have been researchers who are developing a type of simulation based on binary decision diagrams, BDDs. And this borrows a lot of insight and techniques that come from classical electrical engineering circuit simulation. Okay. So up to this point, is there any background questions that I can answer regarding quantum circuit simulation and maybe also these different types of simulation techniques?
Can I ask how you define point 2? Does it extract structure for repeated simulation with different parameters? What does it mean to extract structure?
Let's see. So what does it mean to extract structure, right? So let's imagine that you have something familiar. So what's familiar here? Suppose that you have a circuit that's intended to do something like Shor's, right? Maybe Shor's is not quite the right example either. Suppose it's just like QFT, okay? So if you can, in your head, imagine the QFT circuit, it has a structure, a topology that describes how its gates are connected together. So if you know the QFT diagram, the QFT circuit, the structure would be something like, okay, first you do a bunch of Hadamards, and then you have C0 gates that go from 1 to 1, 1 to 2, 1 to 3, and so on. It has this ladder structure. So that pattern of how the gates are organized is what I mean by structure. Okay, and structure is separate from parameters. So what parameters would be inside, for example, the QFT circuit, the parameters would be, okay, the CZ gates, the CZ gates in the QFT, each of them is taken to a different power. So those different numbers in the actual gates, that's what I refer to as parameters. And so what I'm trying to talk about in this second bullet point here about extracting structure, what I'm talking about is, are you able to, if you know that your quantum circuit has a certain structure, can you leverage the fact that this structure is fixed and do simulations again, but this time, or in the different runs of the simulation, put in different rotation angles? Good question.
A follow-up question for a binary decision diagram. How is that different from control flow diagrams for classical compilation?
So they may have related semantics. So decision diagrams, yeah, you can think about them as like these branching trees. So they're tree-based data structures, where at each node in the tree, you're deciding on different outcomes. And so semantically, they may look familiar if you're familiar with the types of diagrams and control flow diagrams. But in general, this is a big area, and even just within decision diagrams and, for example, control flow diagrams, as you say, there's a lot of different ways to use that basic tree data structure, and use it to represent different types of problems. Okay, good questions. Okay, so the next part, I'm going to start going into a little bit more depth. I'm going to talk about work that I have done specifically in a recent paper that we worked on. And the topic of this is, we're going to leverage these things called graphical models, probabilistic graphical models that come from classical artificial intelligence. And we're going to change the semantics of the artificial intelligence graphical model so that we can use them to simulate the variational algorithms that we're interested in. Okay. And the reason that we're going to do this type of conversion, going from a quantum model like quantum circuits into something that's like classical, like a graphical model, is that this translation process outlined here in 5 steps, the translation process here, each of them uniquely addresses a kind of problem that we need to tackle on the right-hand side here, that we need to tackle in order to simulate variational algorithms. Okay. So I'm going to walk through these compilation stages next, going from a quantum circuit, a noisy quantum circuit, finally to a compiled representation that allows us to query and sample from the final wave function. And doing that is going to be useful, a useful compilation that allows us to do quantum circuit simulation, specifically for variational algorithms. Okay, so let's try to walk through this step by step. So first I'm going to convert quantum circuits, noisy quantum circuits, into Bayesian networks. And so first it's useful maybe to talk about what is a Bayesian network. So Bayesian networks are a type of graphical model that AI researchers have studied for decades, so probably at least 40 years of research going into them. And what they're useful for is they're basically useful for representing cause and effect relationships. So you can have these classical Bayesian networks that represent things that happen in, for example, medical diagnoses, right? So what you would do is you would take a bunch of symptoms, and then from the symptoms you can introduce probabilities that allow you to infer, if you have a certain set of symptoms, what types of underlying diagnoses would explain those symptoms, right? And so in the classical setting, Bayesian networks are completely real valued because their values inside them represent probabilities. But what's interesting is we can actually change the semantics of Bayesian networks from real values into complex valued amplitudes. And a lot of the interesting types of semantics and queries still carry over. And so they are very useful as representations to represent quantum circuits, especially noisy quantum circuits that have both probability-based semantics and also quantum amplitude-based semantics, okay? And so what I'm gonna represent here is I'm gonna show you a simple noisy quantum circuit. So this is a Bell state preparation quantum circuit, right? So you have the Hadamard followed by a C0, and so this leads to the interesting entangled states that that you often see in quantum tutorials. But for this circuit, I'm going to introduce a noise model. So I'm going to put into this quantum circuit a generalized amplitude damping gate. So this is the generalized amplitude damping. It's a kind of noise channel. And basically what it does is once you have the state of qubit 0 at this point, once it passes through the GAD, generalized amplitude damping gate, what it does, it has some chance of flipping it up or also flipping it down. Okay, so it's a noise model. It introduces an unintended gate that wasn't supposed to be there. Okay, and so this is the way that you present it as a quantum circuits. What's unfortunate is that you have these probabilities and also amplitudes, right? So in the amplitude damping gate, you have a probability of it taking place. And then the rest of the circuit, you have amplitude. So these are qubit states. And so what would be nice is if there would be, it would have been nice if there's a type of representation that captures both the real valued probabilities and also the complex valued quantum amplitudes. And what we propose is exactly that type of representation here. So this is a quantum Bayesian network representation of the quantum circuit that we have up here. So we translate from here down to here. And the basic translation procedure is you just take the quantum states that you have, and then you link them according to the dependence, right? So you see here that the Q0M1 gate depends on the Q0 quantum state at moment 0. And so you can build this type of diagram like this. And there are also interesting ways that you can take these types of probabilistic noise models and turn them into gadgets inside the Bayesian network. So that's how you get the structure of the quantum Bayesian network. At the same time, you also have within each node of the Bayesian network, you have these tables that we call conditional amplitude tables, okay? And so these are analogous to the probability tables that you would have in classical Bayesian networks. But in this case, these tables are for amplitudes, and they contain, in general, they contain complex valued parameters. And you can roughly see that these tables, they correspond to the unitary matrices that you would have from the quantum circuit. Right? And so this table here, for example, at the Q0M1 node, that corresponds to the Hadamard gate. So the Hadamard turns into a table looking like this. And then the C0 that you have here turns into a table that looks like this. Okay, and so what's interesting is I've outlined a very nice correspondence between the proposed representation of quantum circuits using Bayesian networks and also the classical probabilistic properties of Bayesian networks. And so a lot of these concepts that we have in quantum computing have analogous meanings or analogous operations and objects in the classical setting. And the key distinctions here are just that we have to turn the probabilities that we have in classical inference and turn them into complex valued amplitudes. And because of that, we're going to have the types of interference and the canceling of amplitudes in the quantum setting that you usually would not get in a purely classical probabilistic setting. Okay. Any questions so far? Okay, so the next stage of translation here is we want to, in these next few steps, we want to go from this conversion of the quantum circuits to Bayesian networks. We want to start using really advanced techniques that we're borrowing from classical AI as a way that we can extract this structure that we're so interested in, right? And so the motivation for this is that in the classical setting, suppose that you had that medical diagnoses Bayesian network that we had imagined before, right? And you want to query that medical diagnosis Bayesian network many times over, but for different sets of parameters. So for example, you have different probabilities for different symptoms and probabilities for underlying diagnoses. And so in the classical setting, researchers have developed these cool techniques that allow you to do repeated queries on Bayesian networks, but for different sets of parameters, just like that, okay? And we're going to borrow those techniques that they used in classical simulation and classical inference, and we're going to use them for quantum circuit simulation here, okay? And so the first step is we're going to convert those Bayesian networks into logic equations, okay? And the motivation for this is more general than actually what we're trying to do, right? In general, it's in computer science, there's a lot of different disparate fields of research where basically we've taken these problems and converted them into satisfiability problems. Satisfiability problems represented as these CNF, conjunctive normal forms. And in this case here, we're outlining the first procedure to take a quantum circuit and turn it into exactly that, a satisfiability problem. And the way that we obtain that satisfiability equation is through the Bayesian network that we had before, right? So we can take these Bayesian networks representing quantum circuits, and we follow the way that they've developed for AI compilation. We can turn them into logical equations such as this. Okay, so these are 5 clauses here that correspond to the semantics and some of the constraints on how qubit states work. Okay. And furthermore, we're going to keep adding more clauses here. So in this slide here, I'm adding 4 more clauses. These clauses talk about how the Hadamard gate works. So these logical equations here encode the mechanics, they encode the semantics and meaning of the Hadamard gate, and we've turned it into a set of logic equations, such as this one. Okay. And we can do that also for the C0 gate here. And we're going to do that for all the nodes in the Bayesian network And we're going to take all of those clauses that outline the rules for each of how each of those nodes work, and we're combining them by conjoining all of those clauses together and turn them into one gigantic CNF. Okay, and so the CNF, all the satisfying assignments, so all the ways that we can satisfy the CNF, they're going to correspond to correct what we call Feynman paths, or correct paths through the quantum circuit. Okay, and if we can sum up all of those Feynman paths, that's going to be equivalent to the problem of solving and doing simulation of the quantum circuit. Okay, is there anything I can mention here to clarify this process for you guys at this point?
What is the efficiency, like asymptotically, of, or runtime efficiency of doing this step, the conjunctions?
So this is the questions about, okay, is this efficient, right? So is it costly to convert Bayesian networks or quantum circuits into CNFs as proposed? So this is very efficient here. So we're just doing the semantics, we're just doing one-to-one translation of the semantics of the quantum circuit. We're turning them into a representation as Bayesian networks that's linearly proportional in size to the quantum circuits. And then we're going to turn them into these logic equations, which again is also linear in size with respect to the Bayesian network. So this part of the translation, we're just doing just like a forward pass. We're just converting the quantum circuits into Bayesian networks into CNFs here. So this part is not costly. Okay, the next part here is going to be the costly part here, though. So the next part is going to be something that's a lot like taking the CNF that we had before, and now we're going to run a satisfiability solver on it. We're going to find all the ways that we can satisfy the CNF, and we're going to compile and represent that representation efficiently using a format called a arithmetic circuit. Okay. And so the basic idea here is these tools, these satisfiability tools, they're able to examine the structure of your quantum circuit. Okay, so this is a naive compilation of your quantum circuit, and it can do a lot of minimization tricks that take you from a naive representation, such as this chandelier-looking thing here, and we're going to reduce it to a more compact representation like this. Okay, and this type of crunching is the brawn and the brains of this compilation, of this minimization. We're borrowing advanced satisfiability solvers that have been honed over decades. We can now, in this case, borrow those satisfiability solvers to do this type of minimization. Okay, and so on the right-hand side here, what I'm presenting is the ability for this compilation approach, the ability for it to crunch down the structure and reduce the representation for various types of algorithms. So I'm plotting the size of the final compiled representation with respect to the size of the quantum circuit here. So this metric of the CNF variables, this represents how big your quantum circuit is in terms of depth times width, okay? And as you see, it's able to extract different amounts of structure for each of these quantum circuits. So for something that's really challenging, like the supremacy circuits, these random circuits, it finds very little structure. Or for something that's more structured and very structured, like Grover and Shor's, it's able to extract some structures and bring down the cost of representing those circuits. Okay. And with this compilation approach, we can now do the task of simulating the circuits with this representation. Okay. And so here I have that Bell state preparation quantum circuit that we had before. We've done the compilation and turned it into an arithmetic circuit shown here. And now in order to do quantum circuit simulation, all we have to do is traverse this tree. And the way that you do this traversal is like this. What you do is you go to the leaves of this tree, and you assign to each of the leaves these input variables, these truth values for each of the observation outcomes. And then you do a percolate up operation. So you just combine the evaluations according to the operations enumerated in the tree. And once you've done this progression, percolate up, calculating values up the tree, you will obtain the correct probability amplitude for that state assignment. Okay. And so we've turned the task of doing quantum circuit simulation from a task of multiplying huge matrices against long vectors. We've turned it into a task of traversing these trees that we've compiled. And more generally, so I'm not going to go into detail about this here. More generally, this type of tree also enables us to do sampling more efficiently via a process called Gibbs sampling. So Gibbs sampling is a type of Markov chain Monte Carlo sampling process. And these trees support those types of simulation queries too. Okay. So any questions about this overview of using arithmetic circuits so far?
Can I ask, CNF to AC is using an SMT solver?
Yeah, so the CNF to AC, this is using, it's not exactly a SMT solver. This is more like a DPL, satisfiability solver. I don't know what DPL stands for. It's a bunch of last names. But the DPL solver, it's also a type of satisfiability solver.
And you said step 4, exact inference on AC, is just traversing the tree?
Right, so step 4 would be, okay, so now that you have this representation, which we assert corresponds to the Bell state circuit, how do we actually obtain the density matrices that we want to have that are the results of quantum circuit simulation? Okay, and so you're able to build these density matrices by traversing the tree, finding each component in the tree, finding each component in the density matrix like this. Okay, so I'm going to present one slide of evaluation outcomes here. So what I'm going to evaluate in this case is I'm evaluating the performance of doing this style of simulation with respect to doing simulation using multiplying density matrices. So I'm going to do this for various workloads. So for the left-hand side here, I'm going to do it for the QA-OA algorithm. And for the right-hand side here, I'm going to do it for a simple VQE quantum physics problem. For each of them, I'm going to plot the time it takes to do simulation on the vertical axis against the number of qubits in the quantum circuit that I'm trying to simulate. And I'm going to plot that on those axes, the time it takes to do density matrix simulation and the time it takes to do knowledge compilation, so our approach to doing the simulation. And as you see, as we increase the problem size for each one of them, after a certain point, the approach of doing this costly compilation upfront, but then performing queries efficiently on that compiled outcome, that technique is going to beat out the naive approach of just multiplying the density matrices. And we see that this is consistent across both of the workloads. Okay. Any questions up to this point? So just as a recap, what I've presented is an alternative way to do quantum circuit simulation based on knowledge compilation of classical graphical models. And more broadly, it addresses the challenge where we want to develop better simulations and better simulators specifically for the workload of these important algorithms that are useful in the near term. So these noisy variational quantum algorithms. Okay, and so I talked about as an overview and as background, what are those algorithms at the beginning of the talk? I talked about what are various noise models. I talked about why simulating these algorithms is uniquely challenging. And finally, I went into detail about how we can use classical AI Bayesian networks to do that simulation. Okay. So this has been the work with my supervisor at Princeton, Professor Martinosi, and also my collaborators at UCLA, who are the experts in a lot of these AI techniques. Okay, so thanks for your time. I'll take any questions about any part of this talk. And we can also use the chat box for questions if you like.
Can I ask, do you think we'll need different simulators for different hardwares? Like, do you imagine we'll have specialized quantum hardware for certain algorithms? For example, like D-Wave's hardware is meant for quantum annealing, and if we're going to see machine learning heavy applications of quantum computing, we might need dynamic context switching versus like just universal quantum computers.
That's an interesting question, right? So I think more underlying question is, what are each of these types of simulators that I outlined here? What are they good for? And yeah, I think exactly the possible outcome of all this type of research is that each of these simulators is going to be uniquely good for a different domain or different domain of quantum computing or a different class of quantum algorithm. And this very much is very, very active field of research. Like there's also different aspects of running these simulators on different types of hardware and different types of classical computers. Each of these addresses a different class of quantum algorithm. And yeah, so the likely outcome is that each of these simulators, they'll all be useful, and each of them will be used for different types of simulations.
Can I ask where, like Bayesian network, the toolchain you mentioned, described where that falls in terms of the time-space trade-off for simulating, for classical computers simulating quantum computers? For example, the Schrodinger simulation technique is much more memory intensive than the Feynman simulation technique, and the Feynman is more time intensive.
So in terms of memory and time trade-off, I would say that our Bayesian network approach, it's most similar in it's most similar to the Feynman simulation techniques, so tensor network contraction techniques, in terms of its time and space trade-off, right? So the reason for that is because we're simulating these quantum circuits by finding one amplitude at a time, as opposed to holding the whole state vector all at once. So that style of finding individual amplitudes, that's a lot more like Feynman simulation, tensor network simulation. Yeah, I believe you have another guest speaker who's going to be talking about quantum computing supremacy. And so in the whole domain of evaluating quantum supremacy, the simulators that they work with there are all in the class of Feynman simulators.